Hey guys, welcome to the second video installment of the Chapter 3, which is Projectile Motion series. As Chapter 1 dealt with some different types of projectiles and how they interact, and we talked a little bit about free fall and the different equations we use and such, and we dissected both the horizontal component and the vertical component of their motion, and this is just a brief overview of the first part of chapter 3. We talked about how the horizontal component is completely constant because there's no acceleration change, no velocity change, which is acceleration, but the vertical component of motion is constantly changing because there's acceleration due to gravity. So that's just a brief overview, but if you need a complete review, please go watch my video on that because it would be very helpful to you. And you need to know that stuff when we move on to this. And as you can see here, we have a beautiful drawing of a cannon shooting a cannonball. The cannonball is the pink thing here. And so we're going to talk about distance when we're talking about free fall, and not so much distance about how far things go, because we already know how to solve for that. We're going to talk about something else, which is ideal path. So you can see here, I've drawn this blue dotted line kind of along here, and I've drawn this orange parabolic or curve, or just curve. And so one key thing to notice is the blue dotted line is the ideal path of the cannonball. It's the path that the cannonball would take if there was no friction, no air friction, and no gravity, okay? And so it would just continue on forever, for infinity. The ball would never fall, and it would keep going in a precisely straight path. Oops, sorry, my mic was away from my mouth. I just realized it might have been a little quiet. But now we're going to deal with when we actually do have gravity affecting it, and so we notice this is free fall. We're not going to deal with the air resistance, just the gravity. So something interesting to notice here is that the distance between the ball on the ideal path here and the ball at the actual path here, the distance between those two here, distance at 1 second, the distance here, d, at 2 seconds, the distance at 3 seconds, and this can go on forever, really, for however long. Well, sorry, just forever, however long. Again, apparently this cannonball took 4 seconds to hit the ground, but if it took 100 seconds, it can go on for 100 seconds. So the distance between these is found by our basic distance equation. D for distance is equal to 1/2 a t squared, and we remember that in this equation a is interchangeable with g. Because we're on Earth, we're going to use g, so we can simplify to the equation to the more common equation. D is equal to 5t squared, because that is 1/2 g is 5. Excuse me. And I'll talk about this equation a little later, but we're going to just plug the numbers in, okay? So 5t squared, it's very easy to solve for this equation. We want to find the distance between ideal path ball, right here, at second 1, the distance between ideal path and actual path ball. Very easy. D is equal to 5t squared, so 5 times 1 squared is 1, equals 5 meters. So let's just write it here. D equals 5 meters. Now let's do it for 2. D is equal to 5 times 2 squared, okay? 5 times 2 squared. D is equal to 5 times 4 equals 20, right? So D equals 20 meters. And over here, running out of room, but D is equal to 5 times 3 squared. D is equal to 5 times 9. D is equal to 45. D equals 45 meters. Okay? So that's basically the distance between ideal path ball and actual path ball. Ideal path is unrealistic. It's what happens without gravity, without friction. So the distance between ideal path and actual path with gravity is simply D is equal to 1/2 at squared, or D is equal to 5t squared. Now I said I was going to talk about these equations. This equation here is used with the A term, only when you're not on Earth, and the acceleration due to gravity is not 9.8 meters per second. Is not 9.8. So we know that here on Earth, our acceleration due to gravity, which is g, is simply 9.8 meters per second squared. But on another planet, it could be anything else. So what we take, oh, and 1/2 of g we call 5 because for simplicity's sake, we use g is 10, just for simplicity's sake, because 9.8 is a rather awkward number to be dealing with in some rather nasty equations. So that's just what we denoted as 10. So, but when let's say we're on Mars, we don't know their, well, I don't know their acceleration due to gravity, just the back of my mind, but I do know that we can't use d is equal to 5t squared on Mars because 1/2 g on Mars is not 5. 1/2 g could be some completely different number. So in that equation, you'd 1/2 at squared, and for a, you'd put other planets g, which is acceleration due to gravity. It could be much lower because their g could be much weaker. You know, you understand, their gravity could be a weaker pull. So yeah, that's basically, like for the moon example, we know that it would be different, right? They don't have the same gravitational pull as us on Earth. So that's something to think about. But now we're going to move on to the next part of the lesson. But keep this, know this. I don't think it comes up too much in later physics. Actually, I know it doesn't come up too much later in this class. But keep this diagram in the back of your head. Know that the distance between ideal path and actual path is found by this equation, or this one, depending on where you are. So now let's move on to the next thing, which is optimal angles. And optimal basically means ideal. We're dealing with the word ideal again. Optimal would be ideal or preferred or best. So optimal angles. Oops. Wow, that's very bright. Did not mean to do that. So when we're dealing with optimal angles or ideal angles, we're talking about optimal angles, okay? Optimal angles, when we're talking about this, we're talking about the best angle for something to be launched or fired or thrown at, for it to get the furthest distance. We want something to go the farthest possible. Furthest possible. Okay. So let's have this little guy, me, throwing a ball. Okay. Say I'm throwing a ball, and I'm not the best artist, but deal with it. Let's say I'm throwing a ball, and I want it to go as far as possible. My friend over here, he wants it to come to him, and it's a far distance. We want to know, well, what angle should I throw it at? Should I throw it at, completely parallel to the Earth? I don't think so. Should I throw it straight up? No, it will come back down to me. So what should I throw it at? Well, the book says that, and it is true, that the optimal angle for projectile is at 45 degrees. So if I throw this ball at a 45 degree angle, it will go as far as possible based on how hard I did throw it. So this angle right here is 45 degrees. Okay, so if I were to throw it at an angle closer to maybe 20. Sorry, this is just not good drawing, and these angles are not correct at all. Actually, I'm going to redo that. Actually, these angles are not, drawn at scale. If I were to throw it at, let's say, 20, it would maybe, fall down right there, and that's a 20. Nothing's to scale here, remember. But then, now we ask ourselves, well, what were to happen if I were to throw it at an angle larger than 45? Would it go further than 45? Well, no, because 45 is the optimal angle, and it's the only optimal angle. So if I were to throw it at 70, it's kind of like this. Interestingly enough, it would land at the exact same spot as if I were to throw it at 20. Just it would go a lot higher, okay? So then that leads yourself to believe, what if I threw it at 25, okay? And it would go a little bit further. So now what if I threw it at 65? So kind of like this. It would go high, and it would land at the same spot as 25. So here's 70 again, 70, 65, 25 here, 25. Now what we need to notice is when angles add up to 90 degrees, projectile D, projectile, oh wow, that was just bad. Projectile D is the same. Just, I'm not going to write the same, I ran out of room. But, okay, so when the angles add up to 90 degrees, the ball you're throwing is going to go the same distance as both, so as if you were to throw it at either of those angles. So I know that's really kind of confusing, but let's look at it. If I were to throw it at 65, it would land in the exact same spot as if I were to throw it at 25 degrees. And this equals, what do you know? It equals 90 degrees, okay? So now, same thing. If I were to throw it at 70 degrees, it would land at the exact same spot as if I were to throw it at 20 degrees. And that equals 90 degrees. Now, 45, right? 45. If I were to throw it at 45, it would land at the exact same spot. Clearly, no, it's very intuitive here. And that's basically the way to check. 45 is 90, and it's going to land at the same spot if you throw it at 45 degrees twice, right? So, and even, yeah, if you're to throw it at 1 degrees and 89 degrees, right? So that equals 90. I mean, 1 degrees is very, not, it's kind of a lame throw, but yes, that's what would happen. And 89 degrees is very vertical. It's almost completely vertical, right? So that is optimal angles, and I'll see you in the last video of chapter 3, which is answering some of the homework problems. And I'll then move on to chapter 4.